Hey guys, this is going to be a video discussing some of the basic trigonometric identities. If you're in my pre-calc class, this is going to accompany Chapter 5, Section 1. If you're another pre-calc class, we're using the Larson book, Precalculus with Limits, a Graphing Approach. And I think we're in the 6th edition. Okay, let's start with an idea of what we're doing today, which is to rewrite trig expressions in terms of other trig functions. That's a little bit hard to grasp for most of you right now because we haven't done anything with it. So let's take a look at some of these before we really understand what we're doing. First thing we need to know is the idea of an identity. In math, an identity presents two equivalent expressions. Two things that have the same meaning, that have the same identity. You already know a trigonometric identity, where tangent is the same thing as the sine divided by the cosine of the same angle. We're presenting two things that are mathematically the same. We mentioned that identities are ways of dealing with two things that are the same. I just showed you that you know some already. The tangent of an angle is equal to the sine of that angle divided by the cosine of that angle. You know some identities that are based on definition. We know that the secant of an angle is equivalent to 1 over the cosine of that angle. The reason that we use these is sometimes some forms of a trig expression are easier to work with. And this might be something that we don't really begin to understand until we're pretty in deep in this. So I'm just going to dive right into some of the basic identities that we're going to be using. And hopefully through some examples in this and the following videos, we'll get to a point where we're more comfortable. The most basic trigonometric identities that we have are the reciprocal and the quotient identities. These are all identities that you already know. You can guess that the top 6 are the reciprocal identities. And if you remember, these graphs were all related by sharing some of the characteristics of the one they're paired with. So secant is connected to cosine, cotangent is connected to tangent, cosecant is connected to sine, and sine is connected to cosecant. We know these go back and forth because of how they're defined. On the unit circle, secant is the same as 1 over x. Cosine is x, so it makes sense that these two are reciprocals. Cotangent is x over y. Tangent is y over x. We can also see that those are reciprocals. You can do the same thing with sine as 1 over y and y. The quotient identities are based again on sine and cosine being y and x. Tangent is just y divided by x, or sine divided by cosine of that angle. Cotangent we know is x over y. Cosine is x, sine is y. We're dealing with the quotient of those two trig functions. The next sets of basic identities are the cofunction and the even and odd identities. The cofunction identities are based on the paired trig functions that are related in large part by translation on the coordinate plane. We've dealt a lot with sine and cosine. We know that their graphs are 90 degrees apart. That if this cosine function looks like this, the sine function is the same graph but shifted over. And if we're dealing with a shift of this graph, we're dealing with a translation of pi over 2 radians. We've used all 6 of these in the last chapter, so I'm not going to go more into depth. Again, these are the cofunction identities. The even and odd identities are related to the even and odd function definitions. Remember that an even function has the property that if I plug in the opposite of x in, so f of negative x, it gives me the same value that f of x does. An odd function is such that if I plug in the negative value, f of negative x, it gives me the opposite, the value of f of x, so negative f of x. And just to quickly take a look at these and verify that they look kind of similar, if I plug in the cosine of negative 60 degrees, I get an answer that's in the positive x coordinate of 1/2. This is the same answer I get if I do the cosine of 60 degrees, which also equals 1/2. We could verify these graphically. We could verify them more surely algebraically, but for now I want you to see that this is true just numerically. Over here I could do the same thing. The sine of negative 45 degrees, for instance, would be, if I'm going down, we're going to have a negative square root of 2 over 2, while the sine of positive 45 equals a positive square root of 2 over 2. And once again, we could verify this algebraically or graphically, but at the moment we just want to verify that these things are true. All of these identities are going to be on the inside cover. I think it's the inside front cover. If you turn over the first page, you'll see them on the back in our textbook. They'll also be typically on the inside cover of every calculus book that you'll take a look at. And for the most part, it's perfectly okay to use them as a reference. That's true for the first identities also. Most of these you're going to begin to be comfortable with, and they're going to become part of your math reasoning. Let's look at a couple examples of where we might use these problems. Okay, if I know that the sine of an angle, so the sine of negative x equals negative 2 over 3, well, it might be nice to know the sine of that angle. And if I look at this a little bit more closely, I can tell based on my even-odd identities that the sine of negative x is the same thing as saying negative sine of x. Okay, so if negative sine of x equals negative 2 over 3, does it stand to reason that sine of x equals 2 over 3? Okay. Based on sine, I can also pretty quickly figure out cosecant, because I know that cosecant of an angle equals 1 over the sine of that angle. Cool. If cosecant of an angle equals the reciprocal of sine of the angle, we know that cosecant equals 3 over 2. The problem also tells me that tangent is equal to 2 square roots of 5 over 5. Cotangent is the reciprocal of tangent. So 1 over tangent of x equals cotangent of x. If I flip this over, I get cotangent equals 5 over 2 square roots of 5. I'm okay with you leaving that as an answer. If someone asks you to rationalize the denominator, we'd be multiplying both the top and the bottom by the square root of 5, which is going to leave us with a result of the square root of 5 over 2. We know that the tangent of x equals the sine over the cosine of the same angle. In this case, we know both the tangent, 2 square roots of 5 over 5, and we know the sine, which is 2 over 3, but we don't know cosine of the angle. With a little bit of algebraic manipulation, multiplying both sides by cosine of x, and then dividing both sides by 2 square roots of 5 over 5, I get 2 over 3 times 5 over 2 square roots of 5 equals cosine x. My 2's are going to cancel to 1. I end up with 5 over 3 square roots of 5 is cosine. I could also write this as the square root of 5 over 3 by rationalizing the denominator. The last thing I need to do is find the secant, which is going to be equal to the reciprocal of my cosine. If cosine is 5 over 3 square roots of 5, secant would be 3 square roots of 5 over 5. Just these two flipped over. A second example that's more algebraic than numeric is going to be based on simplifying a trigonometric expression. If I have a expression that's written with two trig functions, in this case cotangent and sine, sometimes it's possible to simplify them into one. The first thing I might do is take a look at cotangent. I know cotangent can be written as the cosine of x divided by the sine of x. If this thing's being multiplied by the sine of x, pretty quickly I can cancel out. Sine of x divided by sine of x equals 1, and that leaves me with the cosine of x.